Yeah, today we will be discussing about the strain rate during rolling. Generally, see at room temperature, any plastic deformation, it is not having much effect on the strain rate. Only very marginal effect only will be there, which can be peacefully neglected. But when you go to higher temperature, the material, you will see that there is a strain rate sensitivity. Okay? So, it is highly dependent upon the strain rate at which you are deforming. And when the material is passing through this roll, through the roll gap or through the deformation zone, when it is undergoing the deformation, you will find that there is the strain rate continuously changes, and it may reach to a very high value also. So, this point we have to consider it, because the flow stress of the workpiece, it is dependent upon its temperature, strain and strain rate. And the flow stress, since it depends upon the rate at which deformation takes place, we can say that this strain rate is nothing but the d epsilon by dt. So, how this is going to affect, or how this is going to change or affect the, say, based on this, we have to find out where when the material is moving from this inlet to the rolls to the outlet of the roll, each region the strain rate changes, and for all practical purpose, and a mean strain rate is better for calculation purpose. Okay, for simplicity and other thing, but still let us come out at arriving at some expression for the strain rate at each and every point during the rolling process. So, we can approach this considering one is the sticking friction. Let us assume the first is the sticking friction. Assuming sticking friction, and we know that okay, the surface velocity of the roll v is the surface speed, and if you are considering that from a thickness of T I, it is being rolled to a thickness of T f using a roll, using rolls of, say, let us say diameter or r, okay, or radius r. Okay. So, we can say that the effective strain in plane strain. So, that is effective strain under plane strain condition. So, that we can say that that is equal to, say, 2 by root 3 into log T f by T I. Okay. So, that is the strain which you are going to get it, the effective strain. Now, suppose you consider a height of h, so suppose this is a height h of height t, an element during the rolling process. The rate at which this element is compressed, so let us say this is A and B, the rate at which element of thickness T is compressed, that is given by 2 v sin theta, because you take the vertical component of your the velocity component, and then so that is what we are taking. So, and since on the both the sides it is there, so we will find that it is 2 v sin theta, and the rate at which element is deformed. Okay. So, using the general relationship for strain rate, so we can say that strain rate is equal to 2 v sin theta by t. So, that is, since, so, if it is this one d epsilon by dt, that is equal to 1 by h into dh by dt. So, in that case where h is the thickness, so we can write like this, where T is the thickness, where T is the thickness of the element. And from the geometry, we can always get that T is equal to from the exit side. From the exit side, if you just do that, we can get the which we have used it earlier, T f plus d into 1 minus cos theta. Okay. So, where d is the roll diameter, and that is equal to 2 radius, where r is the radius. So, therefore, we can write that epsilon dot is equal to 2 v sin theta by t is equal to 2 v sin theta by T f, where T f is the thickness of the strip at the outlet plus d into 1 minus cos theta. So, this is the relationship for your strain rate. Now, let us for easy calculation, because at every point finding out the strain rate and then doing an analysis is a very cumbersome job. So, rather what we will do is that so, and you see that this strain rate is now dependent upon what is this theta, because here this is the theta where the element makes with the center to center distance between the rolls, the line joining the center to center distance between the rolls. And you should also say that this alpha is the angle of bite. Okay. And maybe at some point you will find that the neutral point is there corresponding to this, the thickness is T n, where the angle subtended at the center between the exit and the neutral point is theta n. So, these are our general normal terms which we are using it. So, let us now find out the mean strain rate. Okay. The mean strain rate or rate of deformation. So, that is mean strain rate, because you will find that at the entry the strain rate is high compared to at the exit. Okay. So, there is a variation in the strain rate, and in that case that is why it is very simple to calculate based on the mean strain rate. So, that is epsilon dot m, and this is obtained by integrating the strain rate is obtained by integrating the strain rate with respect to theta over the length of arc of contact and dividing by the bite angle alpha. See, this is how we are getting. Therefore, now we can write that epsilon dot m is equal to dividing by 1 by alpha into 0 to alpha 2 v sin theta by T f plus d into 1 minus cos theta into d theta. So, that if you do that integration and putting these limits from 0 to n, applying that, we can arrive at this relationship, that is 2 v by alpha d into log T I by T f. So, that way we can get it, and that is equal to v by alpha log T I by T f. Say for small bite angle, if you just this is the larger case, for a small bite angle, a small bite angle will come when the this radius of the roll is large. Okay. So, for small bite angle, we can write alpha is equal to 2 into T I minus T f divided by d raised to half, or T I minus T f by r. So, that also we can write. So, therefore, now we can, if you substitute that, now we can get this relationship epsilon dot m is equal to say V by root of d into T I minus T f into 2 log T I by T f. So, this relationship we can get it, okay, and do some so, this is the relationship we are getting. So, the mean strain rate, by this relationship we can get the mean strain rate if you are assuming the sticking friction. Now, let us come to the case. This sticking friction is much more pronounced at a higher temperature, okay, especially for hot rolling. This is applicable for hot rolling, but when the temperature is very high, it will be sticking friction. But if at a slightly lower temperature is there, and if your roll surfaces are very smooth and other things, then you may end up with a sliding friction also. Okay. So, let us consider the case for sliding friction. So, strain rate during rolling considering sliding friction. Okay, here itself you will. So, in this let us just consider the neutral point. So, the angle corresponding to neutral point is equal to theta. That means, that theta is taken from the center to center, the line joining the center to center between the rolls. So, that we are taking, that is what this theta n. Okay. At the speciality of the neutral point, as we have discussed earlier, is that the speed of the workpiece and the surface speed of the roll, they are same at this one. And if you assume that constant flow, constant volume flow, mass flow, assuming a constant mass flow, that means, from the entry, what was that the volume of the metal which was entering at any section, now it remains the same. The rate of mass flow is same. So, that means, we can say at the inlet now the velocity is V I into T I. So, that is equal to V f at the velocity at the exit finish, okay, into T f, that is equal to the velocity at the neutral point, which is equal to your surface velocity of the roll, into T n, that is equal to V into T at any point. Okay. So, that is what we are going to get it at this point. What is this at this section, what is that thickness? So, at any for the element. So, therefore, now from this constant mass flow rate, assuming we can write say V of the element is equal to V n into T n divided by your thickness T, the instantaneous value of the thickness T, and where V is the, remember, we are not considering this as the surface speed of the, we are considering the velocity of the workpiece. Okay. Mass flow rate, V is the workpiece velocity or workpiece speed, we can say workpiece speed. Suffix and other things corresponding to say I f and n is corresponding to your inlet or out exit or neutral point or at any point here. So, that is what, and T is the workpiece thickness at any location. Okay. So, at the neutral point you will find that the component of velocity V n in the horizontal direction, okay. In the horizontal direction it is related to the velocity by the relationship, say the component of velocity, if V n is the component of velocity V n corresponds to the velocity at the neutral point, okay, in the horizontal direction. So, that means V n h is equal to V cos theta n, and we know that V is this. So, that is equal to V n T n by T into cos theta n. So, let us say that this is equation number 1. So, if the velocity component at A, this is the point A, let us say A and B, the vertical component of the velocity, the vertical component of velocity at A, V A is equal to V sin alpha, because when you are taking this, this velocity component is like this. So, this is V. So, you just take a vertical and horizontal component. So, that it will be V sin alpha. The speed at which this element A B is compressed. So, that is what we have to find out. Now, at what is the speed at which element A B is compressed? The speed at which element A B is compressed. So, that we can say that V P is equal to 2 V T n by T into cos theta n sin theta n. So, that is what we are going to get it. Okay. So, this part now this relationship, when you are going to differentiate it, that is what we are getting. So, therefore, strain rate is equal to your strain rate epsilon dot is equal to 1 by T into V P. So, that is equal to 2 V T n by T square into cos theta n sin theta n. And from that relationship, now if you look at it, since T earlier we wrote it as T is equal to, with respect to your exit side, T f plus D into 1 minus cos theta. When you substitute in that value of T, this epsilon dot is equal to 2 V T n divided by T f plus D into 1 minus cos theta the whole square into cos theta n sin theta n. This is by considering the sliding friction. Okay. So, in this condition, the mean strain rate you can obtain by integrating within the limits, say theta between 0 and theta n. Theta n means it is this one, not theta n, within the limit 0 to your bite angle. Okay. So, mean strain rate okay. So, that and if you just find that for small values okay, is obtained by integrating within say 0 to theta between alpha. Okay. So, for small values of, we can substitute sin theta is equal to theta and theta square is equal to 2 into 1 minus cos theta. So, this we can just put it so that if you substitute that this, we will get it as 2 V T n divided by alpha into 0 to alpha, and then divided by alpha you have to write, into theta into T f plus d into theta square by 2, okay, raised to minus 2 d theta. So, within this, if you integrate, you will get this as, say, epsilon dot m mean flow rate is equal to minus 2 V T n into T f minus T I. So, that is what you will be getting into d alpha T I T f raised to minus 1 cos theta n, and since theta I is equal to, so we can say that T I minus T f by r. Substituting that, we can just get this equation epsilon dot m is equal to 2 V T n into T I minus T f, because this minus sign it will go, by d alpha T I T f. Okay. From that, we can just get this final value as 2 V T n, the thickness at the neutral point, divided by your bite angle alpha into, say, T I and T f into root of T I minus T f by r, which is your theta value, theta I, cos theta n. So, this is your mean flow strain. So, if you look at these two conditions for sticking friction and sliding friction, we can observe certain things, that is the mean strain rate for both sticking and sliding condition and sliding friction. The mean strain rate, one, it increases with a decrease in roll radius. See, for example, see, you will find that with the roll radius, no, so it's as a square root of, that is epsilon dot m is proportional to 1 by root r, we can say. Second, it increases with increase in reduction. This is B and this is C. That is, it increases with the increase in roll speed. That is what we are getting here. See, one is with the reduction increasing, now it is strain rate is increasing with the increase in the reduction, and with your bite angle increasing, what will happen is that this decreases, okay, and with the radius of the roll it is increasing, again it will decrease. So, we can write that with the bite angle. Bite angle has a direct relationship with the roll diameter. Okay. So, these are the main findings from this. So, when you are considering the hot extrusion, hot rolling, you have to consider the effect of strain rate on deformation. Okay. So, now let us come to the next part, few things which are required to be mentioned. Okay. That is a simplified analysis of rolling load, we can just, because otherwise rolling load becomes very cumbersome. So, simplified analysis analysis of rolling load. So, that in a very quick way we can just look at it. So, basically the rolling load is the roll pressure times the area of the contact of the metal and the roll, the workpiece material and the roll. So, that is what it comes. So, if you are able to know what is the roll pressure at each and every point, that is what we have discussed earlier. But if you just neglecting friction, see mainly for thin sheets and other thing, it is always advisable to use smaller diameter roll. Okay. In that case, the friction, total frictional force is not very high, because the contact length is very less. So, that way we can neglect it. So, if the friction is neglected, the pressure which is on the roll is basically the yield strength, okay, yield stress of the material. So, if you neglect friction, the pressure, roll pressure at every point is the yield stress of the material. And the area of contact is can be approximated as the projected area of arc of contact. Arc of contact times width of strip. Times the width of strip. See, for example, if this is your this one, and this is the roll center, and if this is the thing for small radius, no, see this length and the projected is this one LP. So, for larger radius, no, you will find that LP is almost equal to the arc of contact. That is what the thing is there. So, in that case, no, your roll pressure, rolling load P is equal to your pressure P into B into LP, where LP can be approximated as say R into T I minus T F. We can just where LP is equal to root of R into T I minus T F. That is what we can. So, this is equal to say your plane strain flow stress of the material into B into root. So, we can say R into delta T, that is what it is coming, where this sigma naught is the plane strain yield strength, which is equal to 2K is equal to 2 sigma 0 by root 3, where sigma 0 is the uniaxial tensile yield strength of the material. So, this is a very quick way of finding out this one. And when you are using this sigma naught, you have to be very careful. Sigma naught dash is used when there is no spread. So, when there is spread, the uniaxial yield stress sigma 0 is used for P. So, this is a very simple way of finding out that. Okay. Maybe there will be slight error and other things, that is okay, and then this is not considering much of the effect of friction also. This is the basically the rolling load for the deformation purpose. Okay. So, assuming that friction is neglected, especially when you are using a smaller diameter roll and other things, that is what is come. Now, let us come to your defects in the rolling part. Okay. Defects can occur during the rolling as a result of the interaction of the plastically deforming workpiece with the elastically deforming rolls. This is one thing. So, you can have this roll is there is going to be elastic deformation depending upon, especially for higher load, no, this is going to happen. Okay. And then your material is plastically deforming, it also will get work hardened, all those things are going to happen. So, what happens is that due to this non-uniformity will take place. Let us see what are these. See, when there is a very high rolling force, okay, then roll flattening will take place. So, instead of that here, if this is the in fact, it should have been like this, but then you will find that okay, this is what is happening. So, instead of being here, the roll gets flattened because of the elastic deformation. Due to the pressure, the roll pressure, it gets elastically deformed. And then what will happen is that your thickness is not maintained. So, whatever you wanted is that the thickness will always be more than that. Okay. And that is one thing. Second thing is that because of the very high force, you know, this roll will bend. So, this is a roll, this is a roll, this is a roll, and bending of the rolls also will take place, especially when it is a longer roll. And so, due to this, this is basically due to the stiffness of the mill, okay, or the roll. The thickness of the exiting sheet will be greater than the roll gap, which you have done at a no load condition, because before the starting you will be checking at the roll gap and other thing under no load condition, and then only you are fixing. So, in that case when you do it, because of the high roll pressure which is coming, one is that it may slightly deform, and there will be roll flattening which is taking place, and at the same time now there will be say bending also will take place. If bending is taking place, the thickness of the sheet will be not uniform. So, because you will find at the center the sheet thickness is higher than at the edge. So, there will be non-uniform thickness across the section, across the width. Due to roll flattening, the radius increases, apparent radius of the roll will be much higher, and then okay, in that case the contact area will be larger, you will end up with a larger forces. Okay. So, you should know before fixing the roll gap, you should know a priori that what is going to be the deflection of the rolls. So, for that now you should know that the stiffness of the mill. So, stiffness of the mill generally normal range is with 1600 to say 3200 tons per centimeter for screw loaded mill, and maybe for 2500 roughly tons per centimeter for hydraulically rolling mill, loaded mill. So, if you know that, then to obtain a desired roll thickness, we can do the adjustment. Now, there will also be elastic flattening of the roll. It will increase the roll pressure, and is a condition where roll eventually deform more easily than the workpiece. So, that is also elastic flattening will happen. Hence, there will be a minimum thickness below which the sheet cannot be reduced further. So, it is not that okay, you can reduce any amount and other thing. There is a minimum limit, limit in thickness below which the sheets cannot be reduced further. And this limiting thickness is proportional to one, your coefficient of friction, the roll radius, the flow stress of the workpiece, and inversely proportional to the Young's modulus value okay, we can say the mill stiffness. Now, based on this, what are the normal defects which can occur? So, one is the waviness, the wavy edges are coming. See, these wavy edges happens if the see in this condition, if you look now, edges is going to be strained more. So, it is compressed more than at the center. Okay. So, you will find that the edge part there is an elongation compared to that at the center of the sheet, so, means along the width of the sheet, mid widthness region, compared to that the edge will have a more strain, so that it will just deform like that. And then what happens from the center and the edge, it is not uniform. So, which result in say a wavy appearance, especially at the edge. So, that is not advisable. Okay. Then another thing is that if this is going to be very large, so at the center outside now material has been deformed much, whereas at the center that much is not deformed. So, at the center portion resultant force will be a tensile in nature, and if the deformation is very large, that will result in some defects, which is called as a zipper crack, like a zip, it is continuously going on that. So, this is that zipper cracks which are there. So, that can also form. So, in that case, the solution to avoid this is taking into the consideration of this one, you do that crowning or give a chamfer like this. You give a chamfer to roll. It is an exaggerated view which is shown, it will be only very small only. You give a chamfer to the roll, so that at the center, though it is deforming, and when you move towards the edge, you are going to have a uniform deformation. So, depending upon that, you can do how much this chamfering can be done, so that ultimately what comes it will be a flat piece without any wavy structure. Okay. And then there are also chances of cracking, edge cracking can take place, because as the workpiece it passes through the rolls. All elements across the width experience some tendency to expand laterally. When it is passing through the rolls, so across the width, that there also it will have a tendency to expand laterally along the width direction. Okay. But then this is opposed by the transverse frictional stress, and due to the friction hill, if you look at the friction hill, it is high at the center compared to the edge. So, you will find, due to which what happened, the element at the center, the spread at the center region, if you take a small element at the center region, its spread will be much less than when you compare at the edge portion. At the edge portion what happens, it is free to move, so that it can deform there, but whereas the center, it is constrained for the elongation. Okay. And then the thickness decrease at the center, it goes through a length increase, and the thickness decrease, because there is the thickness at the edge decreases much. So, part of that goes to the spread, and since there is a continuity between the edge and the center, you will find that it result in edge cracks. Okay. So, you have a strained tension at the surface here compared to at the center. So, here there is a longitudinal stresses are there. So, tensile stresses are there at the edge compared to a center. So, that may after some time result in say edge cracking. So, that is what. So, center split also can take place, this also can take place. And this edge cracking can also be caused by the inhomogeneous deformation in the thickness direction. Okay. When the rolling conditions are such that, see, suppose you have a thick piece and then okay, your strain is not very high. So, what will happen is that only at the surface only strains are there, reduction is not very high. Then what happens at the edge, the piece was like this, and after some deformation you will find that only at this region only the straining has taken place, at this region. So, that part you will see that okay, it is deformed larger. So, you are getting this, and but with the subsequent rolling passes, what will happen is that this will also end up with say splitting. Okay. The material is not compressed directly, but is forced to elongate by the neighboring material close to this center. Okay. So, this will lead to high secondary tensile stresses, leading to the again this edge cracking. But if you are giving too high reduction, then barreling also may take place, and the limit will come when the surface at the strain at the surface has reached a level where it is going to develop crack. Okay. So, that also can happen. So, there should be some optimum reduction which is possible based on your properties of the material and the working environment. Now, another is this alligatoring part. So, this is also when this part goes to a very high extent. So, this part when it goes to a very high extent, the stresses are again going to come. Okay. So, and this can happen due to curling of the sheet also. So, because if there is going to be a small, if the material is not exactly at the center, if there is a curling of the thing, that can happen when either the surface velocity of the roll, if it is not uniform, then this can happen, because after some time you will find that some displacement, the strains are very high. So, it will just split in this way, and you call it as alligatoring. So, it is like an alligator opening its mouth, that type of shape it is coming. So, basically it is splitting at the center. So, that is what it results in. So, these are some of the defects which are taking place during the rolling operation. If you are not careful enough, so you may have to give some crowning of the rolls, or the chamber has to be provided, so that uniform width or thickness of the sheet is obtained from center to the edge part. And similarly, you have to avoid these wavy edges, the zipper cracks can be avoided, all these things by proper use of the die, and making sure that your inlet material is also uniform thickness, and the roll speeds are exactly the same. If there is a variation, it is going to have split the sample which is going to come out. Okay.